Thanks for joining me for the Anatomy of a Supernova Part 3 timeline, the chaotic final years of a massive star. Modern observations suggest that the last years of some massive stars are far more violent than previously thought, as we've talked about from the two papers that we've talked about. And again, remember, the links are there. If you come over here to EadsyAstronomy, you can get to the papers that way. Instead of quietly collapsing, they may eject shells of gas, erupt multiple times, and create a complex environment before the final supernova explosion actually happens. Here's a simplified timeline of the process. Here you can see a red supergiant. It's just in the stable burning phase. This time scale lasts for millions of years. A massive star spends most of its life fusing heavier and heavier elements in its core. The fusion chain progression is hydrogen to helium to carbon to neon to oxygen to silicon to iron. So again, the fusion chain progression: hydrogen, helium, carbon, neon, oxygen, silicon, iron. Covered this before. We'll just quick review. Each stage becomes progressively shorter in time. So hydrogen, core temperature is about 40 million Kelvin. That lasts about 10 million years, depending on the mass of the star. Helium burning to carbon and oxygen is about 20 million Kelvin, so the star gets hotter. That means its luminosity is going to increase, so that lasts about 1 million years. Then carbon begins to burn into neon, magnesium, and oxygen. That temperature rises there to 6 million Kelvin, and that lasts about 1,000 years. Then neon goes into oxygen and magnesium. That temperature then rises to 1.2 billion Kelvin, and that lasts about a year. Oxygen burns then into silicon and sulfur, and the temperature rises from 1.2 slightly, not as drastic as we've seen before, but up to 1.5 billion Kelvin, and that lasts about 6 months. And then silicon begins to burn into iron. The temperature rises drastically, doubles in intensity, 3 billion Kelvin. That's only for a day. Once the iron core is formed, it will collapse. Temperature rises to 5 billion Kelvin, and that lasts, it says less than a day. It's actually minutes. The actual core collapse happens in just milliseconds, few seconds, milliseconds. Happens very rapidly at that point. Once iron forms in the core, fusion can no longer produce energy. The core bounces, and this leads to the supernova explosion. So the next one, after stable burning, we go into late stage instability. Here you can see a massive red giant, supergiant, shredding out its outer layers into the surrounding environment by it. The timescale for this is years to decades before the explosion. The paper suggests that many stars enter an unstable phase near the end. Possible causes include, just to review, turbulent nuclear burning, core convection instabilities, binary interaction with a companion star, radiation pressure eruptions. During this phase, the star may eject huge shells of gas. These shells create circumstellar material, CSM, around the star, as in that artist's image here. The pre-supernova mass ejections timescale months to years before the explosion. Some stars appear to undergo violent outbursts shortly before their death. Mass loss rates during this stage can be enormous. Typical solar wind is 10 to the negative 6 solar masses per year. So extreme eruptive loss is 10 to the negative 3rd solar masses per year or more. These eruptions form dense shells of gas only a few light years away from the star. Here you can see the massive star on the bottom, recent violent mass ejection, and then a gas shell forms from earlier eruptions, and then earlier stellar wind is the outer shell. When the star explodes, the blast wave will eventually slam into each of those shells. Core collapse happens. Artist's impression of a core collapse going on right there. Seconds. The iron core becomes gravitationally unstable. The sequence of events at that point is the core collapses. Density exceeds that of an atomic nucleus. A neutron star forms, or a black hole. Usually, in this case, it's going to be a neutron star. We get a rebound shock develops. The outer layers explode outward, as the artist's image shows. Typical explosion energy at this is 10 to the 44th joules. It's about the energy of our sun emits over its entire lifetime of 10 to 12 billion years. Collision with their circumstellar material. Here you can see that as the core collapse is now escaping from the star, it's now beginning to interact with the gas around it. This is where things get interesting and where the new papers come in. As the ejecta expand outward, they eventually collide with previously expelled gas. When that happens, a shock wave forms, gas heats to millions of degrees, energy converts to radiation. The result can be rebrightening of the supernova, changing spectral lines, and strong radio and X-ray emissions. From 1987A, you can see interacting with the shock waves, the explosions interacting with shells of gas around it. The interaction can produce multiple peaks in the light curve, which is exactly what astronomers saw in that first paper. Changing supernova type. One of the most surprising outcomes is spectral evolution. Initially, the supernova may appear to be hydrogen poor, type 1b or type 1c. But when the expanding debris hits that hydrogen-rich circumstellar gas, hydrogen emission lines appear. To observers, it looks like the supernova changed type. This is something called a metamorphosizing supernova. Long-term remnant formation. The time scale is hundreds to thousands of years. Eventually, the expanding shock wave will slow down and it forms a supernova remnant. Famous examples of these in amateur telescopes include IC443, Cassiopeia A, the Veil Nebula. I've seen each of those visually. I'll show you in just a second. Okay, many of these intricate filaments seen in these objects are the result of shock waves interacting with surrounding gas. Why these papers matter? For decades, astronomers assumed stripped envelope supernova exploded in relatively clean space. These studies suggest something completely and very different. The final years of massive stars may include violent eruptions, episodic mass loss, dense shells of gas, chaotic environments. When the supernova shock wave hits these structures, we see unusual light curves and a changing spectra. In other words, the explosion itself may only be the final act of a long and violent stellar death process. The amateur tie-in, when you step away from the astrophysics papers and all we've talked here and get back behind the eyepiece or camera, there's an interesting connection to make. The violent processes described in those studies, mass loss, shock waves, circumstellar collisions, are exactly what shape many of the supernova remnants we can observe today or image. For example, the tangled filaments here of IC443 are a classic case of a blast wave plowing into uneven clouds of surrounding gas. In a medium to large telescope or images like the one below, the remnant shows knotty arcs and patches that hint at this interaction. What you're really seeing are shock fronts where expanding debris from the original explosion is slamming into material shed by the star long before it died. Here's an image taken, and here's my sketch, and I have a whole series posted on IC443. This sketch was done back, I think, in 2017, and it just shows just a narrow band that I was able to see, which is pretty typical when I see it visually. The same basic physics is on display in the famous Veil Nebula through a large Dobsonian with an O3 filter, as in the three sketches below that I'm showing here. From my 17.5-inch f44 Dobsonian of the Veil, both the eastern and western components here, the Veil's sweeping filaments trace the expanding shock wave of a star that exploded thousands of years ago. These delicate strands of glowing gas are essentially the cosmic aftermath of the same circumstellar collisions discussed in these research papers. Here's one I did last summer of the Western Veil. One I did back in 2018, I believe, and then here's the Eastern at the same time I did the one above it. Even the compact and turbulent remains of Cassiopeia A, though more challenging visually, and I've seen it multiple times, they tell a similar story. Its chaotic structure is thought to result from a massive star that experienced heavy mass loss before the final collapse. Here's Cassiopeia A from my 17.5-inch Dob. and then an image of Cassiopeia A taken from NASA. So the next time you're observing or imaging one of these remnants from a dark site, it's worth remembering that what you're really looking at. These ghostly filaments and knots aren't just debris drifting through space. They are the frozen record of a star's final violent years, when eruptions and mass ejections filled the surrounding space with gas that the supernova shockwave is still crashing into today. Like I said, I think there's a lot of tie-in from these studies that hopefully we can apply to Betelgeuse, and we can see through Betelgeuse in the next however long before it goes, the story that's going to happen there. It also means we should be seeing some exciting things come out of Betelgeuse and some other stars that are going to go soon. So anyway, I hope you found this as interesting as I do. I hope you can see my passion for it. Love supernova, love observing supernova remnant. They're just an exciting thing to do. Clear skies to you. We'll catch you next time. Thanks for joining me.